The Internet. The Internet is a vast and intricate network that interconnects millions of computers globally, enabling the exchange of data, ideas, and communication across vast distances. Originating from research projects in the mid-20th century, the Internet has evolved into a critical infrastructure that supports almost every aspect of modern life. It facilitates information access, social interactions, business transactions, entertainment, and more. With the advent of technologies like broadband, Wi-Fi, and mobile data, the Internet has become increasingly accessible, impacting societies and economies worldwide. From search engines and social media platforms to online shopping and cloud computing, the Internet's influence is profound and continually expanding, making it an indispensable part of the contemporary world. The Internet has evolved significantly since its inception, transforming from a military communication tool to a global network that connects billions of people. Let's take a look at a timeline of its development. 1960s. 1965, MIT, Massachusetts Institute of Technology, develops packet switching technology, allowing data to be sent in small blocks called packets. MIT is a prestigious private research university located in Cambridge, Massachusetts, known for its cutting-edge research and education in science, engineering, and technology. Packet switching technology is a method of data transmission where messages are divided into smaller packets. Each packet is sent independently over the network and reassembled at the destination. This approach optimizes network resource usage and allows for efficient and reliable data transfer. It contrasts with circuit switching, where a dedicated communication path is established for the entire duration of the transmission. 1969, ARPANET, Advanced Research Projects Agency Network, the precursor to the Internet, is created by the U.S. Department of Defense. The first message is sent between computers at UCLA, University of California, Los Angeles, and Stanford. ARPANET was the first operational packet switching network and is considered the precursor to the modern Internet. Developed by the U.S. Department of Defense's ARPA, and now DARPA, in the late 1960s, ARPANET aimed to enable secure and reliable communication between research institutions. It laid the foundation for the development of Internet protocols and networking technologies. UCLA is a renowned public research university in Los Angeles, California, which played a significant role in the early development of the Internet. 1970s. 1971, Ray Tomlinson develops email and introduces the @ symbol to separate usernames from computer names. Email is a method of exchanging digital messages over the Internet, allowing users to send and receive text, documents, images, and other files. 1972, the first international connections to ARPANET are established, linking computers in the UK and Norway. 1973. The term Internet is coined to describe a network of interconnected networks. 1974, the first Internet Service Provider, ISP, is launched, offering commercial access to ARPANET. An ISP is a company or organization that provides individuals and businesses access to the Internet. 1980s. 1983, the Domain Name System, DNS, is introduced, allowing users to access websites using easy-to-remember domain names instead of numerical IP addresses. DNS is a hierarchical system that translates human-readable domain names into numerical IP addresses used for locating and identifying devices on networks. 1989, Tim Berners-Lee invents the World Wide Web, revolutionizing how information is shared and accessed. The World Wide Web, WWW, is a system of interlinked hypertext documents accessed via the Internet, using web browsers to display content such as text, images, and videos. 1990s. 1991, the first web browser, called World Wide Web, later renamed Nexus, is released. 1993, the Mosaic web browser is launched, making the Internet more accessible to the general public. 1995, the commercialization of the Internet begins, with the launch of major online services like Amazon and eBay. 2000s. 2004, social media platforms like Facebook and YouTube are launched, changing how people communicate and share content. 2007, the iPhone is released, popularizing mobile Internet access and leading to the rise of mobile apps. 2010s. 2010, the first 4G networks are deployed, significantly increasing mobile internet speeds. 4G, fourth-generation, networks provide higher data transfer speeds and improved reliability compared to 3G. 2016, the Internet of Things, IoT, becomes more prominent, connecting everyday devices to the Internet. IoT refers to the network of interconnected devices that communicate and share data with each other over the Internet. 2020s. 2020, the rollout of 5G technology begins, offering even faster internet speeds and lower latency. 5G, fifth generation, networks offer faster speeds, lower latency, and greater connectivity, supporting a larger number of devices and enabling advancements in technologies like IoT and autonomous vehicles. 2023, nearly two-thirds of the world's population uses the Internet, highlighting its global impact. The Internet's journey from a research project to a global phenomenon showcases the rapid pace of technological innovation and its profound impact on society. As we delve into the rich history and milestones of the Internet, it's essential to understand how this global network actually operates on a technical level. How the Internet works. The Internet is a complex system composed of interconnected networks that communicate using standardized protocols. Here's a detailed explanation of its core components and functions. 1. Internet Protocol, IP. The backbone of Internet communication, IP assigns unique addresses to each device, ensuring that data packets are correctly routed from source to destination across diverse networks. 2. Domain Name System, DNS. DNS translates user-friendly domain names into IP addresses, making it easier for users to access websites. It functions like a directory service, ensuring that the human-readable addresses are converted to machine-readable formats required for routing data. 3. Routing and routers. Routers use IP addresses to determine the best path for data packets to travel. They are crucial for directing packets between networks, ensuring that data reaches its intended destination efficiently. Routing protocols like BGP help routers manage paths and make optimal routing decisions. 4. Transmission Control Protocol, TCP. TCP ensures the reliable transmission of data over the Internet. It handles packet sequencing, error detection, and retransmission, ensuring that data is accurately received and reassembled at its destination, providing a stable communication channel. 5. Hypertext Transfer Protocol, HTTP or HTTPS. HTTP/HTTPS protocols facilitate the transfer of web pages and online content between servers and browsers. HTTPS, with its encryption, ensures secure communication, protecting data from interception and tampering. 6. Internet Service Providers, ISPs. ISPs connect users to the Internet, providing the necessary infrastructure for data transmission. They manage the physical and virtual connections between end users and the global network, enabling access to online services and content. 7. Satellite networks. Role and function. Satellite networks play a crucial role in providing Internet connectivity, especially in remote and rural areas where traditional infrastructure may be lacking. Satellites in geostationary, medium, and low Earth orbits, GEO, MEO, LEO, beam Internet signals to ground stations and directly to users. Implementation. Companies like SpaceX, Starlink, OneWeb, and others deploy constellations of satellites to offer high-speed Internet access globally. These networks use advanced technologies to ensure low latency and high throughput. Benefits. Global coverage. Satellite networks can reach areas that are difficult to serve with traditional fiber or cable networks. Emergency connectivity. They provide reliable Internet access during natural disasters or in areas with damaged infrastructure. 8. Modems and network interfaces. Modems and network interfaces enable devices to connect to the Internet. Modems translate digital data into signals suitable for transmission over various media, e.g., phone lines, cables, while network interfaces, NICs, manage the connection between devices and the network. 9. Web browsers and servers. Web browsers serve as the interface for users to interact with the Internet, sending HTTP/HTTPS requests to servers, which host and deliver web content. Servers respond to these requests, allowing users to view and navigate websites. 10. Data centers and cloud services. Data centers house the servers and infrastructure that host online services, applications, and data. Cloud services leverage these data centers to provide scalable and flexible access to resources and storage, enabling efficient data management and accessibility. 11. Content delivery networks, CDNs. CDNs distribute content across multiple servers globally, reducing the distance data must travel to reach users. This improves load times and reliability, ensuring a smoother and faster user experience. In essence, each of these components plays a vital role in the overall functionality of the Internet. The IP ensures correct addressing, DNS simplifies navigation, Reuters direct traffic, TCP guarantees reliability, and HTTPS facilitates content transfer. ISPs, modems, and network interfaces connect users to this complex system, while browsers and servers handle the user-facing aspects. Data centers and CDNs ensure efficient and scalable data management and delivery, creating a harmonious and effective global network. It's the seamless integration and interaction of these components that make the Internet such a powerful and ubiquitous tool in our daily lives. As we've explored the intricate workings of the Internet and its foundational technologies, let's now turn our attention to 5G technology, the next leap in wireless communication that promises to revolutionize connectivity with unprecedented speed, reduced latency, and enhanced capacity, shaping the future of how we interact with the digital world. What makes 5G so special? 1. Enhanced speed. One of the most striking features of 5G is its tremendous increase in data transmission speeds. 5G networks can achieve speeds up to 100 times faster than 4G, with theoretical peak speeds reaching up to 20 gigabits per second. This means downloading a high-definition movie can take just a few seconds, dramatically reducing wait times and enhancing user experience. 2. Low latency. Latency refers to the time it takes for data to travel from its source to its destination. 5G technology significantly reduces latency to as low as 1 millisecond, making real-time applications like online gaming, autonomous vehicles, and remote surgery more feasible and reliable. 3. Higher capacity. 5G can support a vastly higher number of connected devices compared to its predecessors. This is particularly important for the Internet of Things, IoT, where billions of devices, from smart home gadgets to industrial sensors, can operate simultaneously without network congestion. For improved efficiency, 5G networks are designed to be more energy efficient, providing longer battery life for devices and reducing overall power consumption. This efficiency is critical for maintaining the sustainability and performance of large-scale IoT deployments. 5. Network slicing. 5G introduces the concept of network slicing, which allows operators to create multiple virtual networks within a single physical 5G network. Each slice can be tailored to meet the specific requirements of different applications or services, such as high-speed gaming, ultra-reliable communication, or massive IoT connectivity. 6. Enhanced reliability. 5G networks are built to be more resilient, providing consistent and reliable connectivity even in challenging environments, such as densely populated urban areas or remote rural locations. 7. Massive MIMO. Multiple input, multiple output. 5G uses massive MIMO technology, which employs multiple antennas to transmit and receive more data simultaneously. This increases network capacity and improves performance, especially in high-demand areas. 8. Beamforming. This advanced signal processing technique directs signals to specific users, reducing interference and improving signal quality and speed. Beamforming enhances the overall efficiency and effectiveness of 5G networks. These features collectively make 5G a revolutionary advancement in wireless communication, offering unparalleled speed, reliability, and capacity. As we further explore 5G technology, we'll delve into its core principles and understand how these innovative features are implemented to transform connectivity. Core principles of 5G technology. 1. Enhanced mobile broadband, eMBB. Implementation. eMBB focuses on providing significantly faster data rates and higher capacity compared to previous generations. This is achieved through the use of higher frequency bands, known as millimeter waves, which offer greater bandwidth. Impact: this enables applications like high-definition video streaming, virtual reality, VR, and augmented reality, AR, to be accessed seamlessly on mobile devices. 2. Ultra-reliable low-latency communications, URLLC. Implementation: URLLC aims to reduce latency to as low as 1 millisecond, ensuring real-time communication. This is achieved by optimizing network architecture, such as edge computing, where data processing occurs closer to the user. Impact: critical applications such as autonomous vehicles, remote surgery, and industrial automation benefit from near-instantaneous data transmission, enhancing safety and reliability. 3. Massive Machine-Type Communications, MMTC. Implementation: MMTC focuses on connecting a vast number of IoT devices efficiently. This is made possible through technologies like Narrowband IoT, NB-IoT, and Cat-M1, which allow for low-power, wide-area network connectivity. Impact: this supports the deployment of smart cities, smart agriculture, and industrial IoT applications, where thousands of sensors and devices need to communicate simultaneously. 4. Massive MIMO, multiple input, multiple output. Implementation: massive MIMO involves using a large number of antennas at base stations to transmit and receive more data simultaneously. This improves spectral efficiency and increases network capacity. Impact: it enhances the performance and reliability of 5G networks, particularly in densely populated areas, by managing and distributing the traffic load more effectively. 5. Beamforming. Implementation: beamforming directs wireless signals towards specific devices rather than broadcasting them in all directions. This is achieved through advanced antenna technology and signal processing algorithms. Impact: it improves signal strength, reduces interference, and enhances data transfer speeds, ensuring a better user experience even in crowded environments. 6. Network slicing. Implementation: network slicing allows the creation of multiple virtual networks on a single physical 5G infrastructure. Each slice can be customized to meet the specific needs of different applications or services. Impact: this enables operators to provide tailored services, optimizing resources for various use cases like high-speed mobile broadband, low-latency critical communications, and massive IoT connectivity. 7. Edge computing. Implementation: edge computing brings data processing closer to the user by utilizing local servers or devices, reducing the distance data must travel. This is integrated into the 5G network architecture. Impact: it reduces latency and improves the performance of applications that require real-time processing, such as autonomous driving, gaming, and AR/VR. By leveraging these core principles, 5G technology offers a robust and versatile network capable of supporting a wide range of applications and services. Its implementation drives innovation and transforms the way we interact with technology, making it an integral part of the future digital landscape. Having highlighted the unique features that make 5G stand out, it's crucial to understand how spectrum utilization plays a pivotal role in achieving these advancements. Spectrum utilization in 5G. Spectrum utilization refers to the management and allocation of frequency bands used for transmitting data over wireless networks. In 5G technology, spectrum utilization is critical to delivering its promise of enhanced speed, capacity, and efficiency. Here's a detailed look at how it works. 1. Millimeter waves. Millimeter wave. Frequency bands. 5G utilizes higher frequency bands, specifically in the millimeter wave range, 30 GHz to 300 GHz. These bands provide significantly more bandwidth compared to the lower frequency bands used in previous generations. Benefits: millimeter waves can carry more data at faster speeds, enabling high-definition streaming, augmented reality, AR, and virtual reality, VR, applications. Challenges: the higher frequency waves have shorter ranges and are more susceptible to obstacles like buildings and trees. To overcome this, 5G networks rely on a dense deployment of small cells and advanced beamforming techniques. 2. Sub-6 GHz bands. Frequency bands. These bands operate below 6 GHz, including frequencies used in previous generations, such as 2.5 GHz, 3.5 GHz, and 4.9 GHz. Benefits: sub-6 GHz bands provide better coverage and penetration through buildings, ensuring reliable connectivity in both urban and rural areas. They are essential for maintaining a robust and consistent network. Usage: these frequencies are crucial for wide area coverage and are often used in combination with millimeter waves to balance capacity and coverage. 3. Spectrum sharing. Dynamic spectrum sharing (DSS) allows 5G to share the same frequency bands with existing 4G networks. This enables a smooth transition to 5G without the need for new spectrum allocations, maximizing the use of available resources. Benefits: it ensures backward compatibility and efficient utilization of the spectrum, allowing for gradual deployment of 5G services alongside 4G. 4. Carrier aggregation. Concept: carrier aggregation combines multiple frequency bands to create a larger bandwidth, enhancing data speeds and network performance. Benefits: it improves the overall capacity and efficiency of the network, allowing for faster and more reliable connections, especially in high-demand areas. 5. Licensed versus unlicensed spectrum. Licensed spectrum: these are frequency bands allocated exclusively to mobile operators through government auctions or regulatory bodies. Licensed spectrum ensures less interference and better quality of service. Unlicensed spectrum: these bands are open for use by any device without a specific license, such as Wi-Fi frequencies. 5G can utilize unlicensed spectrum to offload traffic from the licensed bands, improving overall network efficiency. 6. Spectrum efficiency. Techniques: advanced techniques like MIMO, multiple input multiple output, and beamforming are employed to enhance spectrum efficiency. These technologies allow the network to transmit more data over the same frequency bands, improving capacity and reducing latency. Impact: spectrum efficiency ensures that the available spectrum is used optimally, supporting a higher number of simultaneous connections and providing better service quality. By effectively utilizing different spectrum bands and employing advanced technologies, 5G achieves its remarkable capabilities, setting the stage for a new era of connectivity. This sophisticated spectrum management ensures that 5G networks can deliver ultra-fast speeds, low latency, and high capacity, transforming how we connect and interact with the digital world. Understanding the role of spectrum utilization sets the stage for exploring another critical aspect of 5G technology: small cells and network densification, both of which are pivotal in achieving the widespread and reliable coverage required for this next-generation network. Small cells and densification. Small cells. Definition: small cells are low-power, short-range wireless transmission systems used to enhance network coverage and capacity in specific areas. They include microcells, picocells, and femtocells, each varying in range and capacity. Implementation: deployed in dense urban areas, stadiums, shopping malls, and other high-traffic locations, small cells work alongside traditional macro cells, large cell towers, to fill coverage gaps and boost network performance. They are typically mounted on streetlights, buildings, and other existing structures. Benefits: improved coverage: small cells enhance signal strength and coverage in areas where macro cells might struggle, such as urban canyons or indoors. Increased capacity: by offloading traffic from macro cells, small cells help manage network congestion, ensuring smooth and reliable connectivity, even in crowded areas. Better user experience: users benefit from faster data speeds, lower latency, and improved call quality due to the proximity of small cells. Densification. Concept: network densification involves increasing the number of cells within a given area to boost overall network capacity and performance. This is achieved by deploying more small cells and integrating advanced technologies like massive MIMO and beamforming. Implementation: in addition to small cells, densification strategies include using existing infrastructure, e.g., utility poles, street furniture, to support new cell deployments, and optimizing the placement of cells to maximize coverage and capacity. Benefits: Enhanced capacity densification allows networks to handle more simultaneous connections, accommodating the growing demand for data and the proliferation of IoT devices. Reduced latency. By bringing the network closer to the end users, densification reduces the distance data must travel, minimizing latency and improving real-time application performance. Scalability densification supports the scalable expansion of 5G networks, making it easier to upgrade and adapt to future technological advancements. The combination of small cells and network densification is crucial for realizing the full potential of 5G technology. Together, they ensure that 5G networks can deliver high speed, low latency, and reliable connectivity across diverse environments, from bustling city centers to remote rural areas. Having explored the critical role of small cells and network densification in enhancing 5G coverage and capacity, let's dive into the advanced antenna technologies that further bolster the performance and efficiency of 5G networks. Advanced antenna technologies. Massive MIMO, multiple input, multiple output. Concept: massive MIMO technology involves using a large number of antennas at the base stations, cell towers, to transmit and receive multiple data signals simultaneously. Unlike traditional MIMO, which typically uses a few antennas, massive MIMO can use dozens or even hundreds of antennas. Implementation: by deploying a large array of antennas, massive MIMO creates multiple parallel data streams, significantly increasing the amount of data that can be transmitted at any given time. Benefits: enhanced capacity. Massive MIMO dramatically increases network capacity, allowing more users to connect simultaneously without degradation in service quality. Improved spectral efficiency. It makes better use of available spectrum, boosting data rates and overall network performance. Robustness. The technology improves signal reliability and reduces interference, leading to more stable connections, especially in crowded areas. Beamforming. Concept: beamforming is a signal processing technique that directs wireless signals towards specific devices rather than broadcasting them in all directions. This is achieved by controlling the phase and amplitude of the signal at each antenna in the array. Implementation: beamforming uses advanced algorithms and antenna designs to dynamically steer the beam towards the intended receiver. This focuses the energy where it's needed most, reducing interference and enhancing signal strength. Benefits: increased signal strength. By directing signals precisely, beamforming improves the quality and strength of the connection, ensuring faster and more reliable data transmission. Reduced interference. It minimizes interference from other devices, leading to clearer and more efficient communication. Extended range. Beamforming extends the effective range of 5G signals, enabling better coverage in challenging environments, such as urban canyons and indoor settings. Millimeter wave antennas. Concept: millimeter wave. Antennas operate at higher frequency bands, 30 GHz to 300 GHz, which offer greater bandwidth and faster data rates, but require advanced antenna designs to manage their shorter range and higher susceptibility to obstacles. Implementation: these antennas are designed to handle the unique propagation characteristics of millimeter wave frequencies, often incorporating beamforming and massive MIMO technologies to enhance performance. Benefits: high data rates. Millimeter wave antennas provide the ultra-fast data speeds necessary for applications like 4K streaming, virtual reality, and augmented reality. Dense deployment. They support dense deployment of small cells, essential for maintaining coverage and capacity in high-demand areas. Phased array antennas. Concept: phased array antennas consist of multiple small antenna elements arranged in a pattern, with each element capable of controlling the phase of the signal it emits. Implementation: by adjusting the phase of each element, phased array antennas can dynamically steer the beam in different directions without physically moving the antenna. Benefits: flexibility. These antennas offer high flexibility in beam direction, making them ideal for applications requiring rapid and precise beam steering. Adaptability. Phased array technology can quickly adapt to changing network conditions, optimizing signal quality and coverage. These advanced antenna technologies are integral to the success of 5G networks, enabling them to deliver on their promises of enhanced speed, reduced latency, and greater capacity. By leveraging these innovations, 5G can provide a more reliable and efficient wireless communication experience, driving the next wave of technological advancements and applications. Having examined the role of advanced antenna technologies in enhancing 5G performance, let's explore the crucial aspect of energy efficiency in 5G networks, which is vital for sustainable and cost-effective operation. Energy efficiency in 5G technology. Green networking. Concept: green networking refers to the design and implementation of network infrastructure and protocols that minimize energy consumption. This is a fundamental consideration in 5G technology, given the increased demand for connectivity and the proliferation of connected devices. Implementation: 5G networks employ a range of techniques to reduce energy usage, including dynamic network management, energy-efficient hardware, and advanced cooling systems. Benefits: reduced operational costs. Lower energy consumption translates to reduced operational expenses for network operators. Environmental impact: energy-efficient networks contribute to lower carbon emissions, supporting global sustainability goals. Dynamic network management. Concept: this involves adjusting the network's operation in real time based on current usage and demand, ensuring that energy is used efficiently. Implementation: techniques such as sleep modes for base stations and adaptive power control are used to reduce energy consumption during periods of low demand. Base stations can power down or reduce their energy use when traffic is low and ramp up when more capacity is needed. Benefits: energy savings. Dynamic adjustments help save energy without compromising network performance. Optimized performance: networks can maintain high performance while using energy more efficiently. Energy-efficient hardware. Concept: designing hardware components specifically for energy efficiency is essential for reducing the overall power consumption of 5G networks. Implementation: modern base stations and network equipment are designed to be more energy efficient, using components that require less power and generate less heat. Benefits: longer lifespan. Energy-efficient hardware tends to have a longer operational life due to reduced thermal stress. Cost reduction: lower energy usage translates into cost savings for operators. Advanced cooling systems. Concept: efficient cooling systems are vital for managing the heat generated by network equipment, especially in dense deployments like data centers and base stations. Implementation: liquid cooling and advanced air circulation systems are used to keep equipment at optimal temperatures while minimizing energy use. Benefits: improved efficiency. Effective cooling systems reduce the energy required to maintain equipment, leading to overall energy savings. Reliability: proper cooling ensures that network components operate within safe temperature ranges, reducing the risk of failures. AI and machine learning for energy management. Concept: AI and machine learning algorithms can optimize energy usage by predicting network demand and adjusting operations accordingly. Implementation: these technologies analyze patterns in network traffic and environmental conditions to make real-time adjustments, such as adjusting power levels or directing traffic to less congested routes. Benefits: proactive management. AI-driven energy management allows for proactive adjustments that enhance efficiency. Scalability: AI solutions can scale with network growth, ensuring consistent energy efficiency even as demand increases. Network slicing and energy efficiency. Concept: network slicing enables the creation of virtual networks tailored to specific applications, each optimized for energy use. Implementation: slices that require lower latency or higher reliability can be designed to use more power, while others can be set to operate in energy-saving modes. Benefits: tailored efficiency. Energy usage can be optimized for different types of network traffic, improving overall efficiency. Resource optimization. Network resources are allocated based on demand, avoiding unnecessary energy consumption. By integrating these approaches, 5G technology not only achieves enhanced performance and capacity but also prioritizes energy efficiency, ensuring sustainable operation and reducing the environmental footprint of network infrastructure. This balance between high performance and low energy consumption is key to the future success and scalability of 5G networks. As we reflect on the intricate mechanisms that make the internet function seamlessly, it's crucial to understand how 5G technology sets itself apart from previous generations. The unique features of 5G include enhanced speed, reduced latency, higher capacity, improved efficiency, network slicing, enhanced reliability, massive MIMO, and beamforming. Now, let's delve into the core principles of 5G technology and understand how these innovative features are implemented to transform connectivity. Spectrum utilization. The role of spectrum utilization is pivotal in achieving the advancements of 5G technology. By utilizing higher frequency bands, including millimeter waves, 30 GHz to 300 GHz, and sub-6 GHz bands, 5G can provide significantly more bandwidth, faster data rates, and better coverage. Dynamic spectrum sharing, DSS, and carrier aggregation further maximize the use of available spectrum, ensuring efficient and reliable connectivity. Small cells and densification. Complementing spectrum utilization are small cells and network densification, which are crucial for maintaining consistent 5G coverage. Small cells, including microcells, picocells, and femtocells, enhance signal strength and capacity in high-traffic areas. Network densification, achieved by deploying more small cells and integrating advanced technologies like massive MIMO and beamforming, supports higher user demand and improves network performance. Advanced antenna technologies. Advanced antenna technologies, such as massive MIMO and beamforming, are essential for bolstering 5G network performance. Massive MIMO increases network capacity by using a large number of antennas to transmit and receive multiple data signals simultaneously. Beamforming directs wireless signals toward specific devices, reducing interference and enhancing signal strength and data transfer speeds. Millimeter wave and phased array antennas further optimize performance in high-frequency bands. Energy efficiency. As we move from performance enhancements to sustainability, energy efficiency becomes a critical aspect of 5G technology. Green networking, dynamic network management, energy-efficient hardware, and advanced cooling systems all contribute to reducing energy consumption. AI and machine learning algorithms optimize energy usage by predicting network demand and adjusting operations, ensuring cost-effective and environmentally friendly network operation. Security and privacy. Security and privacy are paramount in 5G networks. Enhanced encryption and authentication methods, network slicing with customized security measures, and advanced threat detection and prevention mechanisms protect data transmission and user privacy. These security enhancements build user trust and safeguard against cyber threats. Backhaul and fronthaul innovations. Innovations in backhaul and fronthaul solutions are critical for supporting the increased data traffic of 5G networks. High-capacity backhaul solutions like fiber optics and microwave links, combined with optimized fronthaul connections, reduce latency and improve data transmission efficiency, ensuring robust and scalable network performance. Latency optimization. Latency optimization is vital for real-time applications. Techniques such as edge computing, which processes data closer to the user, and optimizing network protocols, reduce latency and enhance the performance of applications requiring immediate data processing, such as autonomous vehicles and remote healthcare. Application-specific customization. Network slicing allows for application-specific customization, creating virtual networks tailored to specific needs. Optimizing resources based on the varying requirements of IoT, URLLC, ultra-reliable low-latency communications, and EMBB, enhanced mobile broadband, ensures that each application receives the necessary performance and reliability. Interoperability with legacy systems. Ensuring interoperability with legacy systems is key to a smooth transition to 5G. Backward compatibility with 4G LTE networks, facilitated by technologies like dynamic spectrum sharing, DSS, allows for simultaneous use of 4G and 5G in the same frequency bands, maximizing spectrum use and maintaining service continuity. Deployment strategies. Deployment strategies for 5G vary across urban, suburban, and rural areas. high-density small cell deployment and the use of millimeter wave frequencies enhance urban coverage, while sub-6 GHz frequencies and strategic small cell placement extend coverage to suburban and rural areas. Addressing deployment challenges with regulatory support and community engagement ensures efficient rollout and broad accessibility. Potential applications and use cases. The transformative potential of 5G extends to various applications and use cases. Smart cities, autonomous vehicles, remote healthcare, and other sectors benefit from the enhanced capabilities of 5G. These applications improve efficiency, safety, and accessibility, driving innovation and improving quality of life. Economic and social impact. The economic and social impact of 5G technology is significant. The deployment and adoption of 5G drive job creation and economic growth, stimulating productivity and innovation. Socially, 5G enhances digital inclusion, reduces the digital divide, and provides better access to education, healthcare, and information, transforming lives worldwide. By integrating these aspects with smooth transitions, we gain a comprehensive understanding of how 5G technology revolutionizes connectivity and impacts various sectors, offering a glimpse into the future of communication and innovation. As 5G technology continues to revolutionize our world, paving the way for unprecedented advancements in connectivity, speed, and efficiency, it's natural to look ahead and anticipate the remarkable possibilities that the next internet generation, 6G, will bring. The predictions for the next internet generation, 6G, are incredibly exciting and transformative. Looking into the future, 6G is expected to provide unprecedented speed and capacity, with data rates potentially reaching terabit per second speeds, which is up to 100 times faster than what 5G currently offers. This leap in speed will support the ever-growing demand for data and enable new, data-intensive applications. One of the most significant improvements anticipated with 6G is ultra-low latency. Future networks could reduce latency to microseconds, making real-time, interactive applications even more seamless. This ultra-responsive communication will be crucial for critical applications, including remote surgery, autonomous vehicles, and advanced industrial automation. 6G will also integrate heavily with artificial intelligence, AI, and machine learning to optimize network performance, manage resources, and ensure efficient data routing. This integration will result in smarter and more adaptive networks capable of responding dynamically to user demands and network conditions. Utilizing terahertz frequency bands, 6G will offer even greater bandwidth compared to the millimeter waves used in 5G. These frequencies will facilitate ultra-high-speed data transmission and support a massive number of connected devices, revolutionizing how we interact with technology. Enhanced connectivity and coverage will be another hallmark of 6G, as the integration of satellite networks with terrestrial networks ensures global coverage, even in the most remote areas. This will provide ubiquitous, seamless connectivity, bridging the digital divide and bringing high-speed internet to underserved regions. The applications and use cases enabled by 6G will be advanced and varied. We can expect innovations such as holographic communication, advanced virtual reality, VR, and augmented reality, AR, experiences, and even more sophisticated IoT ecosystems. These advancements will transform industries like healthcare, education, and entertainment, offering new ways to interact with and benefit from technology. In terms of sustainability, 6G will implement energy-efficient technologies and designs to minimize environmental impact and support eco-friendly network operations. The focus on sustainability will ensure that the benefits of 6G are not achieved at the cost of the environment. 6G networks will be AI native, with AI embedded in the networking equipment, enabling the network to learn and manage itself autonomously. This AI native design will make the network more efficient, adaptive, and cost-effective to operate. The concept of a network of networks will also emerge with 6G, binding terrestrial, cellular, spatial, satellite, air, UAV, and maritime communications into a single, highly dimensional network. This will provide a seamless and highly flexible connectivity experience, enhancing the overall user experience. Lastly, enhanced security will be a cornerstone of 6G, offering robust protection features to ensure that data is secure from unauthorized access and cyber threats. These predictions for 6G highlight its potential to revolutionize connectivity and performance, pushing the boundaries of what's possible with wireless communication and paving the way for a more connected, efficient, and secure digital world. In summary, the exploration of 5G technology reveals its transformative impact on wireless communication, marking a significant advancement from previous generations. Beginning with an introduction to 5G technology, we uncovered its remarkable attributes and capabilities in what makes 5G so special. The core principles of 5G technology laid the groundwork for understanding its innovative features and implementations. Delving into specific aspects, we examine spectrum utilization, which maximizes bandwidth and efficiency, and small cells and densification, which enhance coverage and capacity in high-demand areas. Advanced antenna technologies like massive MIMO and beamforming further boost network performance, while energy efficiency ensures sustainable and cost-effective operations. Security and privacy remain paramount, with enhanced measures protecting data integrity and user trust. Backhaul and fronthaul innovation support the increased data traffic, ensuring robust and scalable network performance. Latency optimization and application-specific customization cater to the needs of diverse applications, from IoT to ultra-reliable low-latency communications. Ensuring smooth transitions and widespread adoption, interoperability with legacy systems and strategic deployment strategies play crucial roles. The potential applications and use cases of 5G span various industries, driving innovation and improving quality of life. Finally, the economic and social impact of 5G underscores its role in fostering economic growth, creating jobs, and enhancing digital inclusion. Looking ahead, the anticipation of 6G technology promises to further revolutionize connectivity with unprecedented speed, ultra-low latency, AI integration, and global coverage. This evolution from 5G to 6G represents a continuous drive toward a more connected, efficient, and intelligent digital future, pushing the boundaries of what's possible in wireless communication. Together, these advancements underscore the profound impact of 5G and future 6G technologies on our world, shaping a more dynamic, interconnected, and innovative global landscape. Please remember to subscribe, like the video, and share it with your friends. Your support is greatly appreciated.